Hi, my name is Nina Flexeder, and as a research associate at the Technical University of Munich, Germany, I've been focusing on the hygrothermal behavior of CLT walls. So in our paper, number 152, we've been monitoring a real office building which has exterior walls made out of cross-laminated timber without any additional insulation layer at all. The office building is located in Austria and was newly built 3 years ago. On the right-hand side, you see a ground floor plan of the first and the second floor, where we have picked 4 different offices that are clad with different wood species. We've placed over 150 sensors in the whole building. However, today I would like to focus only on the spruce-clad offices, specifically their exterior walls facing west and facing north. Here we have placed temperature sensors, PT1000, as well as heat flux plates and sensors for measuring electrical resistance to gather information about the moisture content. So when talking about energy efficiency of any building, what comes to mind is the U-value of the exterior wall. To calculate that U-value, you will usually need to know what is thermal conductancy of the material. That is usually called lambda with the entity of watts per meter Kelvin. And according to code, we should use 0.13 watts per meter Kelvin, which seems quite high, as we do know for centuries that thermal conductancy rises with density and moisture content. And as both might be lower in real life, so could lambda. So our hypothesis is that the thermal performance of CLT might be actually way better than what code suggests. So when analyzing heat transfer through any exterior wall, you can either calculate the U-value based on certain values such as lambda or the thickness of the exterior wall, but you can also measure that in situ. That's what we did. We measured the density of heat flow rate in watts per square meter, which is Q here, and divided it by the difference of temperature of the space inside and outside. A tiny bit different is how to measure the thermal resistance of the building element itself. Here you take the difference of surface temperatures, which might differ from the ones in the space, and divide it by the heat flux density. Using the number of thickness between the 2 points where you measured the density, you are now able to recalculate lambda. So here on the left-hand side, you have a picture where you can see one of our heat flux plates mounted inside, as well as 8 pairs of electrodes that we used to measure the electrical resistance in different depths of the material. On the right-hand side, you can see a horizontal cross-section where we've placed 9 PT1000 sensors in total to measure the material temperature in different depths. Please note that I always counted them from the inside by the distance from the inside surface. On the left-hand side, you have a picture of one of our typical tripods where we have a globe thermometer as well as a sensor to measure air temperature, relative humidity of the air, and CO2 concentration. On the right hand side, you can see one of the heat flux plates that is mounted outside of the wall, as well as another sensor to measure relative humidity and air temperature in immediate vicinity of the exterior wall. So here are the results of the first year. Both sides show the temperature in different depths of the exterior wall. On the left hand side we have the west, and on the right hand side we have the north. So what is striking here is that due to solar irradiation, the temperatures, especially in the outer layers of the wall, may shoot up to 60 or 65 degrees Celsius. That is quite typical and has an influence on our heat flux measurements. When zooming in into 6 random days in September 2019, you can see the typical diurnal changes here as well. And additionally, I've put the heat flux measurements from outside as well as inside of the west and the north wall. Please note that especially in the west, the heat flux measurements outside fluctuate a lot. Here you can already get an idea how difficult it is to gather accurate data for calculating lambda. On the left hand side, you see our results for the simple moving average as well as the cumulative moving average for the heat flux measurements on the west wall. We have to adhere to certain statistical methods that are explained in detail in our paper, and one of the conditions that we should pay attention to is that the difference of temperature inside and out should be greater than 10 Kelvin, so that we get some accuracy there. So most of the year, that's not really the case. Whereas in the northern wall, which you can see here on the right, that time span that is available for evaluation is quite bigger. Another typical influence in any kind of measurements is usually human presence. That's due to their correlation to use any electronic devices, which usually interferes with our measurement devices, and we would like to get rid of any electromagnetic interferences. So here you see the results from our CO2 sensors that we placed in the middle of the room. We do see that we have 3 different time periods. There is normal office use, then there was a 2-week break around Christmas where there was no one in the office at all, and then in spring 2020 COVID started and we had very reduced office use. Unfortunately, a 2-week time period was too short for statistical accurate results. However, those months where most of the people were at home, we could gather some valuable data. We formulated 3 different conditions, A, B, and C, to make sure that our results are statistically accurate. Please refer to our paper. I do not want to get into detail about the math right now. Just to let you know, whenever the deviation was above 5%, we considered the result not accurate enough. That's why it's marked red. So when taken into account all those conditions about statistical accuracy, we end up with the results I show you right here. So I split up the results in regards of the time span where they were taken, and they do differ a bit. On the left-hand side, you can see our results for lambda. It seems that in the West, lambda seems a bit lower. However, all results are somewhat around 0.11 watts per meter Kelvin, which is below what code suggests. On the right-hand side, I've compared the measured U values based on the actual comfort temperature in the middle of the room paired with the exterior temperature. And I've also calculated the U value based on the lambda that I gathered on the left-hand side and compared those. All those values are way below what we would get when adhering to code as well. So going back to that slide where I showed you how lambda differs depending on which raw density and which moisture content you're assuming, our newly found results for in situ measurements show the same range at least. However, right now we are not quite able to draw them back to actual measured moisture content. So this is a research question we're still working on right now, and I would like to take a minute to show you why. So here we have the measurements, or let's say the results, coming from the measurements of electrical resistance within the cross wall section during the whole year. So when doing moisture content measurements, you have to be aware that whenever you leave the range of 25 degrees Celsius, you will have to do something that is called temperature compensation. Like I showed you before, we do have a very high gradient of temperature within very little time spans. So that means we do have to compensate a lot. If I try to get around that by only taking measurements that are taken at time steps where we had around 25 degrees Celsius, this is the results that we get, and we will have around 10% moisture content in both walls. After we submit our paper, we did some in-depth calculations, and we're adhering to temperature compensation, and these are the results from that. I've averaged so that you see some smooth curves here, and you do see that overall moisture content is probably significantly above than what I just showed you, and also it's dipping a bit around spring. So we do see some open questions here still, so that's why we're not able to draw our findings back on actual moisture content in the exterior wall. The coefficient for thermal conductivity lambda is probably around 0.11 watts per meter Kelvin, based on our in situ measurements that we did in the year 2019 to 2020. This was roughly around 1 to 2 years after this building was built, so quite new, and we do assume that moisture content is probably going down with the years, and we are expecting to get different results in a few years. Other than that, we're still working on the technologies to improve moisture measurement in walls with very high fluctuating temperatures. So that's it for now. Thank you very much, and I'm looking forward to our discussion.